Hello everyone, welcome to my video. In this video, I'm going to talk about why the Jacobian, which equals to the determinant of deformation gradient tensor f, equals to the volume change dv over dv naught, where dv is the current volume of the infinitesimal element and dv naught is the the volume of the element in the reference configuration. Okay, in our last video here, that we have talked about the definition of deformation gradient tensor and also how the deformation gradient looks like for some simple deformation cases. And here I will just show this Jacobian why it's equals to the volume change. So I will just skip the definition of deformation gradient tensor in details, but I will just give a short recap. So deformation gradient tensor is defined as the partial derivative of the x vector in current configuration over the uppercase of x in reference configuration, and in the component form is like fij equal to partial xi over partial xj. So that's the definition for it. And given this, so actually there are two ways to show that the Jacobian, which is defined as determinant of deformation gradient tensor, equals to the volume change. Okay, so first let's oops, sorry, there's some problem with the pen. Okay, so first let's review that the general definition of the determinant. So for example, if we have a tensor f, a second order tensor f, the determinant of it mathematically is defined as, so is determined as u here, and this is a cross product over a triple product between uv w. Okay, so this is the mathematical definition, general definition of determinant. And if you recall that what we learned is this. Okay, so what we learned is that because of this equation 1, so we have xi equal to fij times xj, and if we name the that the vectors x consists of like r s t, like this, and also the vector this as uvw. So basically what this means is that we have r, oops, it's just a component. Okay, r equal to f times u. Yeah, it's a vector. And similarly, we have s equal to f times v, and also t equal to f times W. So if this is the case, as you can see that in equation 2, we have this is R, and this is S, and this is T. So basically this is just the dV, and this is just the dV0. Oh, here you should know that the triple product for example, between UVW equal to UV cross W equal to the volume that spanned by these three vectors. For example, UVW. So these two will span a space, and then this will span this, and the physical meaning of this triple product is the volume spanned by these three vectors. Okay, and because of this, that we have this definition, and because of this, if you recall this relation, so this mathematical definition just exactly describes that the determinant of F equal to the volume change. Exactly. So this proves this naturally by the definition of the determinant itself. If we take this F to be the deformation gradient tensor. Okay, and the second one also involves some sort of mathematical concept, but it's necessary. Okay, so this time let's consider still the same element to say. So we name this as 3 as 4. So this is 3, this is 4. Okay, so let's consider this material with uppercase X. So the volume of it, what's the volume? So it's dV0, dV0 equal to basically U times V times W. So du dV times dW, because actually it's for infinitesimal element this works, so I should add a D here. That's the reason. Okay, so this, and recall that. Okay, so here I should introduce permutation tensor. Let's see, what is a permutation tensor? Permutation notation. Permutation notation is not a tensor. So EIJK, let's just call it here. So it's actually it's simply a notation thing. It's positive 1, minus 1, or 0, up to whether it's an even permutation or an odd permutation, or even not a permutation. Okay, so what does the permutation mean? For example, if you have EIJK, that even permutation, or say E123 or E231 or E312, these are all even permutation. And what is a odd permutation? That is like EIKJ, that's odd permutation. And like E132, here this is not permutation. Okay, so an odd permutation would be like KJI or 321 or E321 or E213. This is like a odd permutation. And what is not a permutation is like IKJ. This is not permutation, like 3, 1, 2. Oh, this is 1, 2, 3. Actually, this is a permutation. This is an even permutation. So let's think one. So it's like 3, 1, 1, right? This is not a permutation. And here there's this one. This is not. Okay, and also maybe the 2, 3, 2, something like this. This is not permutation. This is not a permutation. Okay, so okay, if we understand this permutation notation, then mathematically we can show that this triple product is equal to this permutation notation, and then is dui dvj dwk. That's it, right? That's it. And also, there's also another thing that probably I should update, is that recall that if we have two vectors u cross v, what would it become? So it's the permutation ijk times uj times vk. As you can imagine that if we have if I have two vectors u and v, the cross product of these two vectors, I will get a vector perpendicular to the plane spanned by these two vectors, and that's the I direction. This is the j, this is the k. Yeah. So okay, this is just some and here I should have I vector here, right? And so this is just some background to let you know that, so to better understand the triple product, because we have a cross product here. So this is a triple product, and that's why that we have this here. Okay, so this is for the volume of the element in reference configuration. And if we consider the volume of the element in deformed configuration, as we just saw here in equation 3, so we have the r dot rst times dt. This, so what this looks like is similar thing, just change the UVW, just change from UVW to RST. RST. Yeah, that's it. And this is for the volume of the element in current configuration. Because of this, and also we recall, so basically we use the same thing, and recall that we have this thing, so we can write dv as, further we can write, probably we will just write this out, so this dri would be like FIL times UL times DUL, right? From this relation. So similarly, we can write the I is j equal to I of j and dvm, and also dt ijk equal to I of k and dwm. That's it. And now we need to substitute this all into this equation. So what will we get? So what will we get? We get dv equal to eijk the Ri, substitute this one. So we have FIL DUL, and then is DSI, this one. So we have FJ and DVM, and lastly is this one. So here we have FK and DWN. Okay, so that's it. And here now we need to recall one relation, that is this one. Recall that the permutation notation IJK times F IJK RM N equal to ELMN determinant of the tensor. So this is the relation that, okay, so what is this is that permutation notation times this 3 component in the matrix equals to the permutation just times the determinant of the times the determinant of the matrix directly. Okay, so this one is very important. If you recall this one, you just substitute this one to here. As you notice that we have this, and this. So this equation simply becomes dv equal to, so this one is IJK LMN. Notice that this is LMN. So we just simply put this one there. So ELMN DTF. And then we copy the DUL, DVN, DWN from the above. And if you pay attention to this, you will notice that, so this is this, or MN, this is just the, as you remember that this is just like here. This is just the mathematical expression for the triple product. That's the dv0. So we have dv equal to, sorry, my handwriting. We have dv equal to determinant of f times, so this is just dv0. So we have times dv0 as we just shown here. Okay, so because of this, we have this. So naturally, we have determinant of f equal to dv over dv naught. And this determinant of f is called the Jacobian of the determinant, and also called volumetric Jacobian. Or simply the Jacobian of the deformation. Right, and that's it. Okay, in summary, what we have done is, first, we recall the definition of deformation gradient tensor form, and also component form. So in order to show that the determinant of deformation gradient tensor, and also called the Jacobian, equals to the volume change dv over dv naught of an infinitesimal element, we have two ways. First is through a mathematical definition of determinant of a tensor. So this naturally comes, recall that the deformation gradient tensor is defined as this. So if we substitute this just directly into the mathematical definition of determinant, we naturally get dv over dv naught. So this is just from simply the definition of the determinant. And second one is that in second one we introduced the we reviewed the permutation notation and also the cross product. Given this, we can write the reference volume dv naught, and also we can write the dv in current configuration. And dv, because of the relation here, also use the definition of the deformation gradient tensor. We can write the current volume as this one. And recall this very important relation, this. And we substitute this into the dv equation. We can get simply dv equal to determinant times dv naught. And so naturally we got this volumetric Jacobian, are called the Jacobian of deformation gradient tensor J, equal to the determinant of F, and naturally equals to the volume change dv over dv naught per unit volume. Thank you. If you have any questions, please leave a comment, and also comment on what you would like to see in the future. If you enjoyed this video, please click the thumb up and like it. Also share with your colleagues. Alright, with all of this, see you next time. Bye.